Today we are going to perform a topology optimization tutorial with Nastran Solution 200. My name is Christian Aparicio and I will be walking you through today's tutorial. This tutorial is very different from our previous tutorials. Usually when you perform some sort of optimization, you're just optimizing for one analysis type. For example, if you're optimizing for stress analysis, you're essentially optimizing for static analysis. If you're optimizing a natural frequency, you're optimizing for normal modes analysis. This optimization example takes multiple analysis types into account and allows us to perform what's usually named a multidiscipline optimization. So what are we doing by the end of the video? Here is our starting design, if you will. It's a very simple plate. It's loaded. We are going to perform the so-called multidiscipline analysis. We are going to try and maximize the stiffness of this plate as much as possible. We're also going to try and maximize the first natural frequency, while at the same time having a target of reducing the mass by 25%. Now, what are we covering? I'm going to give you some more details regarding this initial design, how it's loaded, material properties, and so on and so on. Then I will cover the optimization problem statement. This is something very critical when you're performing optimization, so I want to give that some time. After this, we're going to go through each step you need to take in order to set this optimization up with Nastran Solution 200. I'm going to talk about how to configure your design regions, your design objective, and your design constraints. We are then going to perform the optimization with Nastran, and then at the end, we're going to have a big discussion on results. I should add that at the very end of this tutorial, I have some additional comments to make. The comments at the end of the video are meant for a new user. If there's some terminology you're not familiar with, if you want to know what the entire workflow for topology optimization is, this will be at the end of this tutorial. But for now, I just want to focus on exactly what the steps are in order to set this up in Nastran. So before getting started, let me just offer my contact information here. My email address is here in the middle of the screen. If you are a professional engineer and you have questions, comments, if you want more training on Nastran Solution 200, please feel free to send me an email with your requests and I will definitely get back to you. Today we are going to use the Nastran Solution 200 web app. This is going to let us set up optimization problems for Nastran. If you are a student or professional engineer, please email me with your request to access this web app. This web app is available. So again, simply send me an email with your request and I will get back to you. So now let's quickly go over the structural model in more detail. Like I said earlier in the video, this is a very simple plate. It's simply supported on edge 1 and on the opposing edge. We have a running load at the midspan of this plate. Now let's quickly go over the optimization problem statement. This entire plate, if you will be the design region. We are going to let the optimizer study this example and let us determine what pieces of the model can be potentially removed. So here our design region will be this entire P shell 1 section. Now let's quickly go over our equation objective. Remember that we want to optimize this plate for both stiffness and natural frequency. So how are we going to do that? We are going to do this via an equation, and that equation would be R0 that you see here. A1 will represent the stiffness or the compliance of this model as it's loaded for the load case. A2 will represent the first natural frequency for this given plate. Now, why are we using this specific equation? Let's quickly go over this. 36.7 is the current compliance for the given load for this current plate. 86.4 is the starting natural frequency for this current plate. Now, when the optimizer tries to minimize this equation, this is what's going to happen. If the stiffness increases, or the compliance increases rather, if the compliance is minimized, for example, A1 becomes 20, and then the denominator equals 36.7. This expression, if you will be less than 1. And now what about natural frequency? If the natural frequency is increased, for example, if instead of 86.4 hertz, it becomes 100 hertz as an example, this also becomes less than 1. So the optimizer will try to minimize both this term and this term on the right. So our objective here is to minimize this expression. When we minimize this expression, we are decreasing the compliance, which is increasing the stiffness, and we are increasing the natural frequency, so we get this term to be decreased. So now let's talk about the design constraints. We are going to have a target mass reduction of 25%. The way we are going to specify this is by saying that the fractional mass should be less than 0.75. We are also going to have a constraint here at the midspan. We are going to say that here you are not allowed to deform more than a -5 millimeters. And then our third constraint will be a natural frequency. We are going to try and minimize, or rather we are going to try and increase the natural frequency as much as possible, but we should at no point be less than 20 hertz. Now here, just to quickly go over why we selected this equation constraint. Here, this equation is as follows. 36.7 is the initial compliance of the current plate. 86.4 is the current first natural frequency of the plate. If A2 is increased, that means that this term will be less than 1. If A1 is decreased, then this term will also be 1. And remember, since we are trying to minimize this entire expression, we want both this component of the expression and this component of the expression to be less than 1, and we also want these two components to be minimized. So again, if we can decrease the compliance and if we can increase our first natural frequency, we are going to be minimizing this objective equation, if you will. Now let's go ahead and talk about the procedure you need to take in order to set this up for Nastran Solution 200. The first thing you need is the starting BDF file. So here, if I go ahead and look in the user's guide, there is a section under topology and topometry tutorials for this example. This one's called Multidiscipline, Static Loading, and Natural Frequency. Just click on this starting BDF file link, and in your downloads folder will be this new zip file. If you look inside of this zip file, you see that the starting BDF files are located here, and this will be our starting point for this tutorial. I should also add that you can build your starting design model in your traditional preprocessor. Here I'm using Patron, so I'll take a quick moment to import the model. Or actually, I'll wait until later to import the model. Here, what I want to say is that you may have your own model you want to optimize for topology optimization. When you are finished creating your model, it will produce a BDF file that you can use as a starting point for your own topology optimization. So now, once we have the BDF file, we need to take the optimization problem statement from 2 slides ago, and we need to express this optimization problem statement in terms Nastran can use. So by this, I mean we have to convert the BDF file, the starting BDF file, to Solution 200. This is where we are going to specify our design regions, our design objective, and our design constraints. After this, we'll go ahead and perform the optimization with Nastran, and then we'll view the results later on in the presentation. So we are going to be using the Nastran Solution 200 web app. This web app allows you to take an existing 100 series BDF file and convert it to Solution 200. Solution 200 is the optimization solution sequence in MSC Nastran. If you want access to this web app, you can email me at this address and I will work with you to get that access. So now let's go ahead and start this tutorial. The first thing I need in order to perform this optimization, I need to combine both of these BDF files. Let me actually say a few comments regarding these two BDF files. These two BDF files are essentially the same. The same plate from the PowerPoint presentation is in both of these BDF files. The same material properties are also in both files. So here, I don't know how quickly I can find the material line. But both of these BDF files share the same BDF file. What I'm saying here is that the same structural model is present in both files. Now, there are a few subtle differences between this BDF file. For example, this BDF file on the left is performing a solution 101 or linear static analysis, whereas the file on the right is performing a solution 103 or normal modes analysis. If we want to perform multidiscipline analysis, we have to merge these two files together. And right now it'll take some time to perform that merging. So step number one for merging, let's go ahead and create some more space here in the case control section. The case control section is between the C end and begin bulk delimiters. After you make this space here, find subcase 1 in this file. Go ahead and let's relocate that to the file on the right. And then we'll rename the subcase 2, just so there's no conflict with this other subcase 1. So far we've moved over the subcase that was for a normal modes analysis. Let's go ahead and make sure that we also bring in the items with the pointers. For example, method 1 is equal to 1. This one is pointing to another entry with identification number 1. So here, let's go ahead and step back here to the right. This one is pointing out to this eigenvalue line that you see here, line 24. You can see the identification number is 1. This line is basically saying what eigenvalue extraction method to use. You'll notice that here on the left, there is no eigenvalue extraction method. If you look through the whole file, there is no entry that's IEGRL. So what we have to do is copy it from the right and paste it here on the right. So now when this subcase is being parsed, method equals 1, Nastran's going to look for this entry with identification number 1. Now the same thing has to be repeated for SPC equals 2. SPC is specifying the constraints or the supports for this model. You can see here in subcase 1 that SPC equals 2 is already present in this file. So if we scroll to the bottom, you should see SPC1, SPC2, here it is. So here line 7436 is SPC equals 2, so that line is pointing to this entry here. And this is then pointing to these other SPC entries that are defining the supports of the model. So since there's already an SPC2 here, we don't have to worry about tracking this pointer since it's already in the model. So we'll go ahead and rename this file Multidiscipline. So this new file contains both all the statements we need to perform a static and normal modes analysis. Now let's go ahead and load this into our web app so we can start the conversion process. So when you're here in the home page of the web app, click on Topology. This is the middle icon. This would take you to the Topology web app. So let's go ahead and upload this new combined file. Remember, this file contains the capability, or rather all the statements you need to perform both a static and normal modes analysis. When you upload the file or your model to the web app, it's going to identify all the properties that can be set as design regions. Here, it's identified pshell1 as a design region. You might be asking, what does this actually mean? Let's go ahead and import the statics BDF file. So we'll go ahead and import that. Or before doing that, I have to make sure that I enable a special option. So here we'll go ahead and select MSC Nastran input options. And then here we'll go ahead and say retrieve names from comments. And then we'll go ahead and mark the checkbox create property and material groups. We'll click OK. We'll select the file here, statics, and click apply. So here you'll notice that here is our plate. Now let's go ahead and identify all the properties in this file. So for this, we are going to go to properties, property name plot. We're going to select the pshell1 here on the right and click apply. So here is the pshell1 region, if you will. This pshell1 is what we want to set as the design region. So here, when we set this as a design region, Nastran will look at this and determine which elements could be potentially removed. So for this, let's go ahead and go back to the web app and pick pshell1. So here is the pshell1 that's been identified. When we click the plus icon, it will go ahead and set that region as a design region. After this, we can then move on to talk about our objective. So here at the top bar, you'll notice that we should first define our variables or objective, then constraints. We're moving on to the objective. Here we are creating a custom equation objective. So we'll go ahead and click on switch to equation objective. And now we can define that expression we mentioned earlier. So the first thing we need to do is define our compliance value. So this value here, when I click the plus icon, will create a new response, if you will, that's called A1. A1 is corresponding to the compliance. Now let's go ahead and do the same for natural frequency. So for the analysis type here, we'll go ahead and switch it to normal modes. And then we'll go ahead and select frequency here. So now A2 is corresponding to a natural frequency. And here we'll go ahead and type in 1. So it's the first natural frequency. So A1 is corresponding to the compliance of the load case. A2 is referring to the first natural frequency. So after we define both of these terms, we can go back up to this equation box and type in A1 divided by the compliance. At this point, we don't know what the initial compliance of this model is, so we'll just include a 1 as a placeholder. And then for the second term, we'll go ahead and type in 2.0. 2.0 is just a placeholder for now. And then we'll divide it by A2. We'll perform a initial analysis just to determine the starting compliance and the starting natural frequency. So we'll use that for 1.0 and 2.0 in a moment. Here we'll go ahead and make sure that we select the minimize. Let's go ahead and now create our constraints. So here you'll see that our first constraint, fractional mass, has already been created for us. We are saying that we want to trim out 25% of the mass, or in fractional mass terms, we want to keep 75% of the mass. Now let's go ahead and define our displacement constraints. So here in this list, look for displacement, click the plus icon, and now configure it here. Now for the component, we are looking to constrain the Z components. So that would be the 3 or T3 component. Now after this, we want to constrain the, let's see, which node did I select here? 714. So node 714 is a node that's here in the midspan. Let me see if I can actually show you which node that might be. And here you can see there are a lot of nodes, 714. So it'll be this node in particular. Let me go ahead and just select it for a moment and then zoom out. So this is the node that we are saying make sure that the displacement at that node is no less than -5 millimeters. So that would be the downward direction. So it would be in the -z direction. Here would probably be a good idea to show you what the load actually looks like for our static case. So here, let's go ahead and show the load. So here you can see the load is at the midspan, and our node 714 is right at the middle. Let's continue on. So 714, -5 millimeters. Let's now create our constraint for the natural frequency. So here we'll go ahead and switch it to normal modes. Here we'll look for the frequency response, and we'll go ahead and click on the plus icon. Here we'll go ahead and say that the first natural frequency should always be greater than 20 hertz. And now let me go ahead and see anything else we should do. Okay, let's move on to subcases. This will take some consideration. So fractional mass is known as a global quantity for this plate, if you will. By this, I mean this plate will only have one mass ever. If you create a new version of the design, it will have a different mass. A natural frequency, or rather volume, is another example of a global quantity. So since fractional mass is a global quantity, it's independent of a subcase, we should apply this as a global constraint. So we'll go ahead and mark this checkbox. Now, the displacement constraint is applying to a static subcase. If you recall, subcase 1 is the statics subcase, so we'll go ahead and mark that checkbox so the displacement constraint is applied to subcase 1. Now, subcase 2 is the normal modes subcase, but the web app doesn't know that immediately, so we have to go ahead and manually set that subcase as a normal modes subcase. Once we do that, we can then mark the checkbox for the natural frequency constraint and assign it to subcase 2. One other thing too, remember that the objective is in terms of A1, the compliance for static subcase, and A2, a natural frequency for a normal mode subcase. It's very important to specify that here in this next section, optional A, configure DR span. This is because if you're dealing with 10, 20, 100 load cases, you need to specify to the equation where the compliance value is coming from. So here I'm saying that for A1, the compliance, that value will come from subcase 1. And for A2, that value is going to come from subcase 2. You can imagine if we had 100 subcases, this list would be pretty long, but at least you can go ahead and select which subcase that quantity is coming from. Now, once we're done here, we need to have a setting. Remember that for the equation objective, we added placeholders of 1.0 and 2.0 for the compliance and natural frequency. We don't know those values yet. So under settings, we are going to say that just perform a one design cycle. What we want to do is have the initial analysis go through first. From there, we'll go ahead and look at the quantities, and we'll use those quantities back in the web app. So let's go ahead and move to the exporter and click on option 1, auto execute MSC Nastran. This is going to download a package. Let's go ahead and extract this package to our desktop or downloads folder, and then we'll go ahead and start this optimization procedure. Remember, we set design or maximum number of design cycles to 1. We do not want a full-blown optimization at this point. We just need to run the first analysis in the optimization so we can determine the first compliance and natural frequency. So here, let's go ahead and go back to the topology web app and click on results, click on responses. Here, we'll go ahead and manually upload the F06 file. So here we are just interested in the initial design cycle. So let me go ahead and type that in. We are looking for A1 and A2. Here you can see A1 is reported and A2 is reported here. In the subcase column, you'll notice that A1, this A1 value is coming from subcase 1. This A2 value is coming from subcase 2. Remember, this was specified when we were configuring the DR span here. A1 is coming from subcase 1. A2 is coming from subcase 2. If you're on the verge of optimizing for 20, 40, 50, 100 subcases, this is a pretty useful piece of information here. So once we've tracked A1 and A2, which are the compliance and normal modes respectively, we notice that the value here for the compliance is 36.788. We'll go ahead and copy that and go back to the web app, go to the objective, look for the equation objective, and we'll go ahead and paste this value here. Remember that this value here is the initial compliance for this model. We'll go back to responses, and then we'll go ahead and look for A2, which is the natural frequency. Here you can see it's 86.43 hertz. We'll go ahead and copy that and replace it with the 2.0 that we have here. And then here we'll go ahead and delete the plus symbol so it's the proper format for the web app. Once we've done that, we can go ahead and perform a full topology optimization. So we'll go ahead and click on settings, and we'll go ahead and set the maximum number of design cycles to 50. And now we'll go back to the exporter and click option 1, auto execute Nastran. That's going to download a new package, if you will. Like before, we'll go ahead and extract the contents, and inside of that, we'll double click start MSC Nastran to start the topology optimization. And now we'll go ahead and give this a few moments. While the optimization is happening, this is a great time to go over the topology optimization workflows. So after this video, I want you to be aware that there are multiple ways of performing topology optimization. One method is very common today. I call this the traditional approach. There's also a second method of doing things. This second method was available in MSC Nastran 2016, I believe. So it's worth covering in this video briefly. Now here, what we're doing is the following. We're starting with our original design. We are performing our first optimization that you see here circled in red. After we look at the topology solution, we are going to refine this design. You can see that the topology solution has a lot of rough edges. You have these corners that could cause stress concentrations. We're going to refine the design, and then we are going to perform a final verification analysis to make sure that the quantities such as von Mises stress, displacement, and natural frequency are less than or within our limits, essentially. So again, the topology solution is going to give us a rough concept like you see here in blue. We are going to smooth it out. We're going to redefine this concept, if you will, and then we're going to perform the verification step after that. Now, let's suppose that you go through this process and you find out that at the end, like this example here, so let me draw our line. Let's suppose that you targeted a mass reduction of 40%. So that would be equivalent to saying FR mass is less than 0.6. And then you perform this refinement of the design. You then perform your verification analysis, and then you find out that your von Mises stress and your displacement are beyond your limits. So this entire topology solution is not adequate. With the traditional method, you are to create multiple topology solutions. So here, this should actually be 0.9 here. So this one's targeting a 10% mass reduction. This one's targeting a 25% mass reduction. And then this one was targeting a 40% mass reduction. So again, you should perform multiple topology optimizations at different fractional masses. You should go through this procedure of creating a refined design and then a verification. Out of all the designs that meet your constraints, basically select the most minimum in weight, and that is your solution. So here, for example, this topology solution reduces the mass by 10%. This next solution reduces the mass by 25%. Since this solution and this solution meet my constraints, I'll go ahead and pick the least weight design, and by the end of this is my solution that you see here. Now, there's also another method of performing topology optimization. Let me go back and discuss the optimization problem statement. Here, you can see that the objective is to minimize the compliance, or rather, maximize the stiffness. Usually, you see optimization work the other way. The objective is to minimize the weight, and the constraint is a displacement, stress constraint, natural frequency constraint. But here, we have it backwards. We want to minimize the compliance, but we're going to constrain the mass of this design. With the latest topology optimization method available in MSC Nastran 2016, we do the optimization in a more logical fashion. The objective is now to minimize the fractional mass, which is saying minimize the mass. Your constraints can now be stress constraints, as an example. I won't cover this in this tutorial, but if you want to learn more about this type of optimization, I will refer you to the user's guide. So let me go ahead and take you there right now. If you go to the user's guide and refer to the topology optimization tutorials, this example here called minimizing mass with stress and displacement constraints, this is the tutorial you want to refer to if you want to use the latest method of topology optimization. But for this tutorial, we are going to focus on the traditional topology optimization method. So going back to the web app, let's go ahead and see the results of our optimization. Here we see that this run terminated due to hard convergence. So this is indication, marked by the green checkbox, that the optimization went through successfully. Let's go ahead and see where the objective is at. The objective started at a value of 2. This makes sense because A1 at the beginning was 3.6 and A2 at the beginning was 8.6. So 1 plus a 1 equals 2. So that makes sense. And then by the end, it minimized the combined value of that equation to 1.2768. So here, if I upload the newest F06 file, and then we go, that's the wrong one. Let's go ahead and upload the newest F06 file. You notice that if we go to the very end, which is design cycle 14, we have A1 equal to 17.383 and A2 rather equal to 11 or 110. If you plug in both of these values, both of these final values into this expression, you will get, according to this, 1.257768. Let's go ahead and now take a look at these results in our post-processor. So here, once you confirm that you have run terminated due to hard convergence, let's go ahead and take the normalize constraints, if you will, or densities, I should say. So under tools, click on post-process. In the directory where the optimization was performed, there is a .des file. This contains the final normalized densities for this model. The normalized densities can be considered element ranks. If the value of this rank is close to 1, that means you should keep that element. If the element is close to 0, you could potentially leave that element out of your final design. So here, let's go ahead and select that DES file. And then after we attach it, we'll go ahead and go to display results. We'll select this design and we'll apply a threshold of 0.4. And here, let me double check my presentation just to make sure I'm using the correct threshold. The threshold of 0.4 is basically saying keep any element with the normalized density greater than 0.4. So remember, the normalized density is a rank. Here what I'm saying is we're saying anything greater than 0.4 is an important element that should be kept. That's what we're saying here when we are typing in 0.4 and clicking apply. So here is the topology solution. You'll notice a few things here. Some of the elements, or the topology solution rather, is very rough. This is where you then have to perform a refinement on this design. You smooth out these sharp corners, you add elements where your judgment says there should definitely be elements there. Then you perform the verification step. So here, let me go back to the PowerPoint slide and show where we're at right now. So right now we have set up our topology optimization. We have a topology solution. Now we have to create this refined version of the design. Now this in itself, I have a feeling most individuals who are seeing this video are well versed on how to create finite element models. So just for the sake of time, I'll go ahead and show you the new refined model, and then I'll perform the verification analysis just to show you. So here, let me go ahead and import this new design I created earlier. So here's our new design. Let me go ahead and actually analyze this new design. It's configured the same way as before. It's using the same loading. It's using the same supports, if you will, same materials, except this time I've already gone ahead and taken time to smooth out many of these elements. So let's go ahead and look at the new results. We are dealing with 836 steel, so the yield stress is actually 250 megapascals. Let's go ahead and make sure that the von Mises stress is under that. So von Mises stress, I'll go ahead and turn off averaging. And here you can see that the maximum stress here is 150 megapascals, which is well under the von Mises yield stress. So this new design has satisfied our constraints. This is an acceptable solution. And just a quick reminder before we conclude this video, you will have to perform multiple topology optimizations. The one we performed is this version here. So let me go ahead and mark this with the red box. Here, we were fortunate enough that once we performed the refinement, after we performed our verification analysis, our constraints were satisfied at the end. Up here, I didn't perform the natural frequency check, but you can trust me that this was also satisfied with this design. Here, this next design on the bottom, this one I performed earlier too. This one, unfortunately, did not meet our design requirements. So this design, unfortunately, did not work. If you ever get caught in this situation, just go ahead and aim for a different mass target. So right now you might be wondering, how do I perform? How do I create these other optimizations here and here? So that's a good question. Let's go ahead and jump out of here. And let's go back to the web app. So here we have this set up to have a target mass of 75. So it's going to keep 75% of the mass. If we export this, we will call this 70% mass target. But this is 75%, so we'll go ahead and say 75. And then we'll go back to the web app and we'll go ahead and change this to 0.9. So this one is a 0.9 or 90% mass target. So we want to keep 90% of the mass and trim out 10%. This one we will call 90% mass target. And then we'll go and repeat the process for the next one. So here, the next one's a 60% mass target. So we'll change this to 0.6. So this one will be trying to remove 40% of the mass. So 60% rather, percent mass target. And then we'll create a new folder, ABC. And we'll move these three there. So here are the three topology solutions or topology optimizations that we should run. So here is A, B, and C. So like before, you extract, you then start MSC Nastran, and this will start the topology optimization. You repeat the process for each additional version of this topology optimization. So after each topology solution here, you then refine the design and verify. You compare the designs and take the better of all the ones. So that is essentially the end of the tutorial. Here's the resulting accepted solution for this example. When you're doing topology optimization of your own, and if you get a different design from what I have here today, it's okay. The whole goal is to get a better design, not the same design as me. You'll find out that when you're refining the design, it's pretty much up to your judgment to decide where elements could be removed and where elements could be left. What's important about topology optimization is that it gives you a good conceptual design from which to start from. So now, with that, that's essentially the end of this tutorial. I'll leave my contact information here if you want to go ahead and reach me. Again, if you're a professional engineer and if you have a question, here's my email. If you're a student or engineer and you want access to the web app, you can also email me at this address and I will work with you on giving you access. Now, as promised, there are some additional slides I wanted to go over in the appendix. If you're new to topology optimization, some of these terms might be useful to you, so I wanted to give some time for this. So let's go over one of the most commonly asked questions. What are the design variables in topology optimization? So now let's go ahead and look at this design. So it's the same example we just performed. Just know that the design variables are known as normalized material densities. You might be asking, what is a normalized material density? So this entire plate, for example, has a density of 1,000 kilograms per meter cubed. Now, I don't know if this is how much steel weighs. It's actually different. But for the sake of argument, just imagine that this is the density, 1,000 kilograms per meter cubed. And this is for the entire plate. With topology optimization, it splits the density into hundreds, thousands, millions of densities. Each element now has its own density, and here I'll say it's density I. This will be expressed in a density that is normalized. So here I'll say it's density normalized. And if I remember, this will be the density of the element divided by the original density naught. So if you have, say, a normalized density of 0.5, then the density of that element is 500 kilograms, and the original density is 1,000. So throughout the optimization process, each normalized density will be augmented. So this density element, I don't know, 50. I don't know what the element number here, 50 is just an example. It will either minimize the density or increase the density. At the same time, some other element 4, the optimizer would decide if the density should be increased or it should be decreased. And this is what happens at the end. You get this range of normalized density values. Some of these values are very close to zero, like you see here in white. So then you can say these regions that have very, very small normalized densities, you can effectively remove those elements. Whereas if you have a strongly colored region where the normalized densities are close to 1, this is a region where you should definitely keep the element that's there. Now, another common question, compliance. What is compliance? If you open the F06 file, refer to this section called element strain energies. Here you have this line that says total energy of all elements in the problem. Since we only have one load case, we only get one strain energy here. So you'll notice that the value for strain energy is 18.39. Keep this in mind. And then further down in the initial analysis, the compliance value is 36.788. The total strain energy is half the compliance. So this is the relationship. It's basically, or rather, compliance is a measurement of the total strain energy in your design for a given load case. Here, there's some additional verbiage that you can go ahead and read if you want additional reference regarding compliance and total strain energy. Here are some steps regarding how to output the element strain energy, just in case you're curious and want to see for yourself. And now, another commonly asked question, what is fractional mass? One thing you'll notice when the optimization starts is a reduction procedure. At least I will call it a reduction procedure. Here at the very beginning, let's suppose that this structure that you see here has a density of 1,000 kilograms per meter cube, like before. So let's go ahead and say that. And we'll go ahead and say that each element here starts at a normalized density of 1. So here, the density here is 1,000. The density here is 1,000. And so on and so on. Now, before the optimization occurs, there's a reduction. If you said that the FR mass should be less than 0.75, or 0.3, as an example, it's going to reduce all of the normalized densities to 0.3. And now, what is the repercussion of this? Here, if the densities were 1,000, it would reduce everything to 300 kilograms per meter cubed. Here, we reduce the density to 300 kilograms per meter cubed, and so on and so on. So here, what you notice is that if all the densities are reduced to 0.3, then here the total mass is 30% of the original. So that's what fractional mass is how much reduction at the beginning should be performed. And throughout the optimization, what mass reduction should be preserved throughout the optimization. So here, if you want to reduce it to 0.3 and then keep it under 0.3, then you would say that the FR mass is less than 0.3. And remember, we specified this in this example. If you look back at the web app, we went to constraints and we said FR mass is 0.6 here. Here, what we're saying is reduce the initial design, reduce the densities by 40%, or rather keep 60% of the original densities and maintain that mass for the remainder of the example here. So here is the start, if you will, the start of the optimization. Remember that during the optimization, it's going to decide if it should increase or decrease the normalized density. Here is another example where it's decreased 0.3 to 0.1 and so on and so on. So if the original design had 6 units of mass and the starting topology had 1.8 units of mass, you see by the end, here I'll say final. Although there are different normalized densities here, since we said that the FR mass should be less than 0.3, it's augmented the density such that you preserve this constraint. And here by the end, you still have a total mass of 1.8 units of mass. So that's what fractional mass is. And here is just a quick repeat of what I said at the beginning. You might be wondering how exactly are we increasing the stiffness from the initial design? How is it possible that if we started with the original density, is the program adding more density to our starting point? And the answer is no. Remember, it's starting with your original density and then reduces. Here, there should be something here like a reduction. There's a reduction. So you can imagine this is a softer version of this design. It will then increase or decrease the stiffness depending on the problem statement. So here as an example, here you can see the spheres are smaller than the squares. This is a reduced version. This is where your optimization starts from. And then you can imagine that the optimizer will size the normalized densities so you can determine based on these ranks, if you will, which elements should remain in the model and so on. And then here, if you want to know how to see the optimization solution, again, you open Patran, you specify the threshold. Here, the threshold is 0.4. So here we are saying that anything above a value of 0.4, so that's around here. So everything here is to be capped. And everything from less than 0.4, that means you ignore, so ignore. So I believe that is the last slide on this presentation. I hope you found this useful. As always, if you have any questions or comments, my email address is at the bottom of the screen. Thank you for watching.